My name is Simon, and it's a joint work with my PhD colleague Jørgen Skålnes and our supervisors Henrik Andersson and Magnus Stålhane. And the nice thing about being the last talk on the split problem is that I don't have to introduce the problem. So let's just go straight to the motivation. Here we go. The starting point is that during this fall, we worked on the production routing problem, and then we made a math heuristic for it. And during that work, we developed what we call a route improving model as part of the math heuristic. And we had this feeling that this model can be useful for solving other routing problems. So our research question was basically, can this improvement model be efficiently used to find good solutions for the split VRP? And why do you think that? Well, we played it around a little bit with on the CVRP. We basically gave the best known solution to the improvement model, and then we were able to find new best known solutions for 6 out of 10 of the largest CVRP instances. So we thought, oh yeah, promising. Maybe we should try this on the split VRP. So our plan was basically just to construct a feasible starting solution that should be pretty good. And then we give the routes. Hopefully you can see my mouse. And then we just give the routes from this starting solution to the improvement heuristic. And then for a number of iterations, we try to improve it. So that was our plan. Unfortunately, we ended up spending so much time on the IRP track that we kind of run out of time for the split delivery. So we had to come up with something really fast to implement for constructing a feasible solution. So what we did is just that we went for a pre-split idea, which has been proposed by many others for the split problem. So we basically just split a customer into S splits, and then we just solve it as a CVRP. And the question when you do this is, how do we distribute the demand? And that would be fun to come up with our own splitting rule. So what we came up with was this formula here. So I'm just going to demonstrate how it works with an example. So say that we have this node here, node number 1, and then we want to split it into S splits. In this case, in 6 splits, and demand is 60. Then the formula for each split would be this. So we can see it's kind of like increasing for each split. So hopefully in this way we can make a lot of different combinations of splits. We kind of thought it would be that most nodes would, if they would be split, they would be split into 2 nodes. That was kind of our original thought. So with this formula, then this would be the different splits, but we round down each of these calculations. So these numbers here add up to 56, and then we just add the missing 4 items to the largest split. So that's basically what we did here. And then we just gave it to the Vidal's HGS solver, gave it 450 seconds, and that was our starting solution. And then we wanted to see, can we use this improvement MIP? And what it basically is a modified path flow model. And what we call path flow model is what Stefan in the last talk is called a route-based formulation. And it's basically that you have a set of routes and you have your problem, and you choose from among these routes, and you choose between them, and then you just give, and then you calculate what you should deliver to each customer. But the problem with this our path flow model is I say that you almost have the perfect routes. There's just one that's a little bit off what it should be, and then the model is kind of used. Then you can't find a good solution. It's a bit odd. Is there any easy way that you can make a path flow model where you can make small alterations to the routes in case you almost have the perfect routes, but you just there's just maybe a node missing or something like that. So that's what we wanted to do. So as I said, here we have a pool of routes or a set of routes or whatever you want to call it. And then if you look at each route in this set, let's say this route here, which we call route R. We already went through this part in our IRP presentation. So sorry for those guys that haven't seen this part again, but I'm just going through it again in case some people missed that presentation. So basically, what we do is we have a route which we get from our construction algorithm. And this route starts in the depot denoted 0 through customer 3, 8, 2, and 0. And then we have to associate this route with a cost. And what we basically do is that we create a cost for kind of the marginal cost of inserting a customer into this route. So the marginal cost here for route 3 would be the cost from going to 0 to 3 plus the cost of going from 3 to 8 minus the cost of going from 0 to 8. And then we calculate this for all the nodes in the route. And then the route cost, or the cost associated with the variable, which decides if we should use this route or not, is calculated in this way. And we can see that it adds up to, we get this C from the cost of going from 0 to 8, and from 3 to 2, and 8 to 0. And if we choose to use this route, we have this variable YR, where R is our route. And if we set this to 1 to this variable is 1, then we have to use the route. But we also have a variable associated with each customer. And if we set these costs to, if we choose to include them, for instance, if we choose to include customer 3, then it's XR3 equals 1. And we can see if we want to keep the original route, we set all of these x's to 1. And the cost related to each x are these costs here. And we can see then that if we take these costs and plus it on these expressions here, then the route cost we end up is just the normal route cost, the cost of going from 0 to 3 through to 8, 8 to 2, and 2 to 0. So basically, so if we just use the route as it is, the route cost is perfectly calculated. And if we want to remove a route now, a node from the route, let's say we want to remove this node 8, just to put it to 0. And this is our route. Then the cost of the route we end up with then is also perfectly calculated. So let's go back to the original route. But one thing is that we cannot remove 2 routes in a row, because then our cost structure will break down. And this is actually a problem on the split VRP with these instances, because as some of you might have noticed, many of the instances in the split VRP that we use for the split VRP problem, they break the triangle inequality all the time. So often say that you wanted to add this node 8 here, and then you just end up adding node 3 as well, because it's cheaper to go to buy node 3 and then to 8, even though you don't deliver anything. And then it's kind of a problem, because if you want to remove route 8, you probably wanted to remove route 3 as well. So that's kind of a problem for the split VRP here that we didn't think about. So basically, what we hear is we have an expression that if we choose to use this route here, then XR3, XR8 both have to be at least one of them has to be 1 for the model to be legal. But we can also remove nodes. Sorry, not remove. We can also add nodes. And let's say here we wanted to add node 9. And node 9 can be inserted into this route in different positions. And what we basically see here is that the cheapest, let's say the cheapest place inserted is between now node 3 and 8. If we do that, we set this XR9 to 1. And the way we have set up the model, the cost of inserting then node 9 between node 3 and 8 is also perfectly or exactly calculated. But it requires that both node 3 and 8 is also included in the route then, because if not, the cost structure breaks down. And another thing is that, let's say that one node also wanted to be the cheapest place inserted greedily was between node 3 and 8. Then we cannot in place both of them, because also then the cost structure breaks down. So we can, as you can see, we can make some alterations to the routes, but there are some limitations. And the limitations that we have put in is basically just to keep the model small enough that it's actually solvable. And this model here can give us the route to the left here was our original route. And you see all these different routes here are routes that the model can spit out. So yeah, we can make some alterations. And one thing that we added for the IRP is the possibility of adding clusters. Say that you wanted to add this cluster here, consisting of route 9, 7, and 9 into the into the route. Then we added the possibility of doing that as well. Unfortunately, we was going to do this for the split VRP. There was a bug. We had a bug that we wasn't able to figure out before the timeline. So unfortunately, this possibility wasn't added into the solver for the DIMACS challenge. But I tried it now later, so we'll look at the results to see how much, if it actually helps. So let's go to the results. Yeah, we came in 4th place, which we are pretty happy about. So yeah, so a relevant question now: was there any point of using this improvement model, or did it actually improve the solutions from our construction algorithm? Well, 57 out of 95 instances were in fact improved, and 19 out of 38 instances that were not improved were already best known solution that if you look at all the solvers. So most likely it might not have been able to improve them anyways. So 19 instances, for 19 instances, there was a possibility of improving our original solution, but the model could not. So yeah. And then I started thinking, what if we had just spent the entire 30 minutes in the construction phase instead? What if we just, because now we spent 450 seconds in the construction phase. Would it be just better to spend all 30 minutes there? No, it would not. We would have gotten considerably worse solutions. And now I was planning to see now that after the competition, I'm going to have some more time to see if can we improve our ideal a bit more. Unfortunately, I didn't have that much time to do it, but I fixed the bug with that we can insert clusters and changed a few of the parameters a little bit. And then we were able to improve some of the solutions there. And actually for ST21, we were able to find the best known solutions of all the solvers. So that was a little bit fun. But if we compare it to the score then to the other solvers, we're still far away from the best solvers. So I think I can spend the next month trying to change parameters and play around. And we would still never be able to compete with the best solvers. So to conclude, can the route improving model be efficiently used to find good solution for the split delivery VRP? Well, our conclusion is maybe. I don't think we have tested it enough to really conclude. It's probably too slow to be to run it many times. But if you had a better construction solution, maybe at the end to run it, maybe it would be a good idea. We'll see. We are planning to play around with it a little bit more to see if it actually helps. And that was that was all I had. The production routing paper where we use this where we introduced this improvement model, it will hopefully be accepted soon. There's a preprint available online. Thank you. And if there are any questions or comments,